next problem is called binary search. We are given an array of integer nums, which is sorted in ascending order. And an integer target, we have to write a function to search the target in nums. If target exists, we have to return its index. Otherwise, if we don't find the target inside the input array, we just return -1. We have to write an algorithm that runs in a logarithmic runtime complexity. So just traversing the array would lead us to linear time complexity, if we would traverse and just check for each element if it matches our target, and if it does, we would just return. But we have to reduce this complexity to the logarithmic one. And in the first example, we are looking for the target 9, and as we can see here, it is at the index 4, so we just return the index 4. In the second example, we have target 2, and it doesn't exist inside the nums, so we just return -1. For the constraints, the nums length is ranging from 1 to 10 to the 4th, and all the numbers inside the nums array are ranging from -10 to the 4th to the 10 to the 4th. All the integers in nums are unique, and the numbers are sorted in ascending order. The numbers are sorted in ascending order is crucial to solve this problem in logarithmic time complexity. Because it is sorted, we can utilize binary search algorithm to find the target in a logarithmic time, to find it, or basically to check if it's not inside the array. So the first thing that we have to do is we have to declare low and high. Those are our initial boundaries. So at the beginning, low is pointing at the first element, the start of our search, and the high is pointing to the end, basically the last element. So at the beginning, we have the whole exploration space. The whole array is basically all the elements are candidates to be matching our target. And let's just put the target that you are looking, as in the example 1, is the number 9. Now for the how do we search for the target 9? You could imagine a dictionary, and if it's sorted in like alphabetical order, if you're searching for a word, and then if you open a random page and you are at the page that lists words that are beginning with M, if you know that you're looking for a word that starts with B, you know that like all the pages after the page M to Z are basically not important to you. So you can discard the whole half of the dictionary and only concentrate in the first half. The process also, if you keep on like randomly choosing a page, basically the process will lead you to the correct page that you're looking at, because each time you're basically discarding a half of elements, or like some random distribution here. So basically, the binary search algorithm first initializes the low and high boundaries, and then it uses those to find the mid element for which we are to which we are comparing our target. So low and high, we will use low and high to find the mid element. So we'll just divide their sum by 2, and in this case it will be 5 divided by 2, which is 2. So we are looking at the element at the index 2, and in this case it's the element 3. And we know that when we compare the element 3 with the target 9, 3 is smaller than 9. So for us it doesn't, because the array is sorted. For us it doesn't make sense to continue our search in the left half of array. Basically, we know that if the target exists, it will 100% not exist in the first half of the array. So we have to push our low boundary and basically reduce the space, the exploration phase space that we are searching our target in. And to reduce the boundaries, to reduce the space, we are moving our low that's pointing to the first element. We are moving it past the element that we just checked, because 3 is not equal to the target. We know that this part is not important for us. Next, we will continue doing this until low is larger than high. So as long as low is basically smaller or equal to high, we will continue this process. So here we have low equal to 3 and high is basically the same. So we will have 5 plus 3, which is 8, divided by 2, which is 4. So we are checking with the element at the index 4, and in this case, the element is 9, which matches the target. So we just returned that index 4. If we didn't hit this element, we would still see if we can discard 1/2 of the current exploration space. And we would do that by just checking if the current element that the mid is pointing to is smaller or larger than the target. If it's smaller, that means that if the mid element at the mid is smaller than the target, we know that we don't have to check any elements from low to mid anymore. We can discard that half. In the case the array element at the index mid is larger than the target, then we don't have to check any elements from mid up to the high, because they will be in sorted ascending order. And if the current mid is larger than target, then we have the only chance to have the element equal targets. It's in the left side. The right side is basically all elements are larger than our target. Now, the number of times that we can halve an array is given by logarithm of base 2 to the number of elements in the initial array. And because when we are doing the calculations, estimation of the time complexity, we can omit the base. So we basically have a logarithmic time complexity. For space complexity, we basically have constant, because we are not creating any additional data structure. At the beginning, we will declare our low and high. Low is pointing to the first element, and the high is pointing to the last element. Next, we will define our loop invariant, which basically means in each iteration of the loop, this condition will be true. The low will be smaller or equal to the high boundary. Then we will calculate our mid, and there are two ways to calculate it. So we can either sum up the low and high and divide them by 2. But if high is a really huge, like a really large number, and when added low, it overflows, we would have a problem then. To cope with that, we can just use the different formula. We can add the difference of high and low divided by 2 to the low boundary. This is basically calculating the distance between high and low, and then adding it to the low, which basically is their average. Next, we check if the element at the current mid is equal to target. If it is, we just return that index. And if it's not, we will have to first check if the element at mid is smaller than the target. And if it is, we know that the mid is basically larger than any element from low to mid. So there is no reason for us to check those elements, because all of those elements will be smaller than the target. So we basically push our lower boundary to the index after mid. In the opposite direction, we would have mid that's larger than the target. And because mid is larger than the target, all the elements between mid and high are larger than the target. So it doesn't make sense for us to look in the right side. So we basically push our high boundary to the element before the mid, and we are looking only on the left side. If we don't find the element, and we basically break the loop invariant, low is now higher than low is larger than the high, we know that there is no element in the nums array that matches the target, so we just return -1.